Hello and welcome to my presentation on weather conditions and climate change with ClimateWins. My name is Jackson Lanier and I'll be discussing the use of supervised machine learning algorithms to predict weather data. This presentation serves as an interim report on a project where machine learning is used to predict the consequences of climate change. So you might be asking yourself why you should care about this project. Increases in extreme weather events over the last 10 to 20 years have prompted ClimateWins to investigate climate and weather. ClimateWins is a fictitious European nonprofit created for the purposes of this project. However, the weather and climate concerns discussed are very real. As mentioned in the introduction, ClimateWins' concern for our future has spawned a project that aims to use machine learning to help predict the consequences of climate change. The data used for this project consists of weather observations from 18 weather stations across Europe. Station locations include Madrid, Stockholm, and Budapest, among others. The data has been collected by the European Climate Assessment and Dataset Project and includes daily observations from 1960 through most of 2022. The observations measure a number of variables including precipitation, humidity, and temperatures. The dataset appears to be complete as it contains no missing values. At the end of this presentation, I'll provide a link to my GitHub where you can access this presentation file and download the data yourself if you'd like. An important part of any project is considering potential bias in the data. There are several forms of potential bias present in the weather data used for this project. First is the possibility of temporal bias. Data collected over 60 years ago could suffer from the outdated tools and methods that don't hold up to today's standards. Second is a potential historical bias. As previously mentioned, extreme weather events have increased in the last 10 to 20 years. If data from the last 60 years is used to predict future weather, there is a risk of inaccurate predictions due to the rapid climate changes occurring in more recent data. Third is the possibility of selection bias based on the location of the weather stations where the data has been collected. The weather stations are likely located in more developed areas of Europe, leading to overrepresentation of these areas in the data and underrepresentation of less developed areas. Further investigation will need to be done before this bias can be confirmed. Though several possible biases have been discussed, this list is not exhaustive and there could be additional biases present in this data. During this project, several hypotheses have stood out as areas requiring further investigation. First, I believe that there is a correlation between rising temperatures and extreme weather events such as heat waves and significant levels of precipitation. As I explore historical data from machine learning algorithms to use in weather prediction, the rise of temperatures across Europe stands out as a concern and could be tied to the increase of extreme weather. My next hypothesis is that weather prediction accuracy will vary depending on location due to climate conditions in each location. Some locations will have more consistent climates suitable for prediction, while others will have varying climate patterns, making weather more difficult to predict. My third hypothesis is that no single machine learning algorithm will stand out as a clear best choice for predicting weather. Certain algorithms may predict weather with more accuracy depending on a number of factors, such as prediction location and the amount of testing put into the algorithm. As with any hypothesis, these hypotheses will require further investigation before any conclusions can be made. The first step of using machine learning to predict weather was to optimize data on the average temperatures of several weather stations using gradient descent. During this process, iterative optimization was able to minimize the loss function to nearly zero. This showed that the temperature data of the different locations can likely be predicted by differentiable functions. The graph on the right displays a gradient descent loss function for Madrid's average daily temperatures during 2021. As iteration increases, the loss function approaches zero, indicating convergence. Next, the k-nearest neighbors algorithm was used to predict unpleasant weather days in 15 of the European weather stations. Using a k-range value of 3, the model was able to predict pleasant weather days with an average accuracy of 88%. Take a look at this chart on the right. The first column under accurate predictions shows accurately predicted unpleasant weather days. The second column under accurate predictions shows accurately predicted pleasant weather days. The false positives column shows inaccurately predicted unpleasant days, and the false negatives column shows inaccurately predicted pleasant days. The k-nearest neighbor algorithm accurately predicted all of Sonnenblick's days as unpleasant, which is 100% accurate because Sonnenblick is located on a mountain in Austria and has 0 days where the temperature allows for what is considered pleasant weather. Sonnenblick is likely causing overfitting in this model because of the noise caused by its complete lack of pleasant days. Continuing with my exploration of supervised machine learning algorithms was the use of the decision tree model. As with the k-nearest neighbor model, the decision tree model was used to predict pleasant weather days in 15 of the European weather stations. Assessing the performance of the model showed around 46% accuracy in both the training and testing data. This visual of the decision tree shows its level of complexity, suggesting that the model is overfitting by classifying everything into its own categories. The tree needs to be pruned back to reduce complexity and capture more general patterns in the data. The final supervised learning model explored was the artificial neural network. As with the last two models, the artificial neural network model was used to predict pleasant weather days in 15 of the European weather stations. In an attempt to improve the performance of the model, several tests were run, with each test tuning the hyperparameters of the model by adjusting hidden layer count, node sizes, iterations, and tolerance levels. The maximum testing data accuracy achieved in 4 different tests was 51%. The training data accuracy for this test was 61%. Training data accuracy consistently outperformed testing data accuracy, which can be a sign of overfitting. The image on the right displays multiple confusion matrices of the 51% accurate testing data results. It is likely difficult to read an individual matrix, but they each represent a different location. In each location, the upper left box displays accurate predictions of unpleasant days. The upper right box shows inaccurate predictions of unpleasant days. The lower left box displays inaccurate predictions of pleasant days, and the lower right box displays accurate predictions of pleasant days. As with the other models, the artificial neural network model accurately predicted no pleasant days in Sonnenblick, which likely contributes to overfitting in this model. After exploring 3 different supervised learning algorithms, I currently believe the k-nearest neighbors algorithm is the best for predicting future weather. This is based on the algorithm having a higher accuracy than the decision tree and artificial neural network models. However, I do think that with appropriate tuning, the artificial neural network model could perform at higher levels of accuracy than seen in the testing done up to this point, and could possibly outperform the k-nearest neighbors model. In summary, I'm hypothesizing that this project will reveal a correlation between rising temperatures and extreme weather events, as well as weather prediction accuracy based on location. Additionally, I believe that no single algorithm will reveal itself as a clear best choice for predicting weather. So far, this project has focused on using temperature data from across Europe to explore different supervised learning models for predicting weather data. The temperature data was optimized for several locations using gradient descent. The K-nearest neighbor, decision tree, and artificial neural network machine learning models have been tested for their use in weather prediction. The next steps of the project will include continued exploration of algorithms to improve prediction accuracy. This could involve removing outliers such as Sonnenblick. This will also mean incorporating unsupervised machine learning algorithms into predictions. Variables other than temperatures such as precipitation levels need to be explored. Keep in mind that the ultimate goal of this project is to make predictions on future weather, which is an integral part of dealing with the consequences of climate change. Thank you for viewing this presentation. If you have any questions or would like to discuss this project further, please send me an email. Additionally, please check out my GitHub for a repository on this project containing the Jupyter notebooks used for my analysis, as well as repositories of my other projects. Last, I'd like to thank Slides Carnival for providing the PowerPoint template used in this presentation. Thanks again.